Okay, in this video we're going to look at a few problems, more advanced type of problems, and then we're going to look at some of the chemistry of sulfur analogs of ethers, commonly known as sulfides or less commonly known as thioethers. Okay, so here are the two problems that we're going to have. Both of these involve epoxides in some way. How are we going to accomplish these transformations? Okay, what these transformations have in common, let's just call this carbon attached to oxygen alpha, and that one beta. Okay, same thing here. What you'll notice that both of these problems have in common is that there's something major happening at the beta carbon, which technically, if you look at the starting material, is unfunctionalized. And we're going to see how we can use epoxides to accomplish this goal. Okay, all right, so I'll go ahead and draw the alpha and beta here again. All right, recognize that we need to add some carbons to the beta carbon. And if you look at the carbons you need to add, they're right here, these three carbons here that are formally an allyl group. Okay, so we need to add an allyl group to the beta carbon. We know that we cannot add anything to the beta carbon as we see it there, right? Because that's just a methyl group. It's not functionalized in any way. All right, so how can we make the beta carbon into some sort of functional group? All right, so what we're going to do is we're going to perform a dehydration. A dehydration now gives us a functional group at the beta carbon. It's an alkene, but an alkene is not the one we want. We really want a leaving group of some sort. So we're going to convert the alkene to the epoxide shown here, known as styrene oxide. All right, and now the Grignard is going to be basically a source of alkyl anion. We're going to add our nucleophile here, in this case allyl Grignard reagent, and followed by aqueous workup to protonate our alkoxide, and that is going to give us the product. Okay, the same problem exists in the second problem here. Okay, we somehow or another need to put a hydroxy group on the beta carbon, but again, it's unfunctionalized, so that presents a little bit of a dilemma to us. All right, so how are we going to do this? Okay, same general idea. We're going to perform a dehydration that is going to give us the alkene. And we now have a functional group at the beta carbon. Again, it's not the functional group we need. We need some sort of oxygen there. Recognize that this structure here, our final structure, looks to be like it's the product of an acid catalyzed ring opening. Okay, and that has the ether group at the more substituted carbon, or the carbon that's better able to form a carbocation. All right, so we're going to make the epoxide, and we're just going to now treat it with HCl dissolved in methanol. That's going to accomplish the acid catalyzed epoxide ring opening. Let's just review the mechanism there. So remember that we're going to protonate the epoxide. We'll just abbreviate phenyl as pH. Okay, and now our methanol is going to come in. All right, we're going to lose the extra hydrogen. And that's going to produce our final product. Okay, all right, let's look at another one. These are not necessarily really hardcore ether problems. These are kind of general Grignard addition problems. Okay, so the first one, how do we convert this alcohol into this compound. Recognize that the alcohol is not really the right functional group for adding a carbon there. Okay, so what we're going to do is we're going to turn, okay, let's look at it retrosynthetically. We know the last step is likely going to be ether formation. Okay, so we're going to deprotonate this hydrogen with sodium hydride, a really strong base, and we're going to add methyl iodide, and that's going to give us the final product. All right, we need to add, however, this alkynyl group to the alcohol. How do we do that? Well, we can't add it directly, but we need to oxidize it first, okay? So this is the product of adding a Grignard reagent to an aldehyde, right? This is a secondary alcohol. That's always made, or often made by Grignard plus aldehyde. Okay, and we know that there's a really good synthetic relationship between this aldehyde I have shown here in brown and the starting material, right? All we need to do is oxidize it with a suitable oxidant that'll stop at the aldehyde stage, like pyridinium chlorochromate, which we usually abbreviate PCC. All right, so let's look at this bottom one here. Design synthetic routes to this one, okay, and part of it is we're going to use Grignard reagents or ketone aldehydes as a source of extra carbons. Notice that we have an extra carbon. There are 6 carbons there. However, here we have 7 carbons. Okay, so we're going to have to add an extra carbon. Recognize that it's going to be much easier to add it at this end than at the other end, right? Because the other end already looks like we want it to look in the final product. Okay, all right. So we need to make a Grignard reagent out of the alcohol. How can we do that? All right, so let's think about this retrosynthetically. Likely a carboxylic acid is the product of a vigorous oxidation of a primary alcohol using one of these stronger oxidants right here. The primary alcohol that has one more carbon than the starting material, this is a general disconnection where we're going to think of formaldehyde plus Grignard always gives us a primary alcohol with one additional carbon. Okay, all right, so there's our Grignard. How do we make that Grignard reagent from that alcohol? Obviously, you can't make it directly from an alcohol. You need to turn the alcohol into a bromide first and then treat that with magnesium, okay? All right, so this is the answer. We're going to convert the alcohol to a bromide, make a Grignard reagent from that, add the extra carbon by treating that Grignard reagent with formaldehyde, and then oxidizing the primary alcohol that we get out of that second to last step. Okay. All right, so sulfur analogs of ethers are known as sulfides. Okay. Sulfides, because sulfur does not engage in any sort of hydrogen bonding, these lone pairs here don't really make good hydrogen bonds, so these are nonpolar. There's no hydrogen bonding. Okay. If we take the simplest thioether of them all, dimethyl sulfide, we find that it's rather low boiling, 37 degrees, and there's no water solubility at all for this compound. Okay. Ether or sulfides can be oxidized, and there are 2 hypothetical oxidation products. It's a sulfoxide is when we add 1 oxygen like so. And there are 2 resonance forms you commonly see written. Important thing to note is that it is tetrahedral. And that even if you draw it this way, it's It's not isoelectronic with a ketone. Okay, so in this latter resonance structure, we've taken advantage of the fact that sulfur has low-lying 3D orbitals that we could use to expand the octet. Okay, it's always important to remember that a sulfoxide is tetrahedral in the geometry of sulfur. Actually, if you had different R groups here, interestingly, this would actually be a chiral compound, and the lone pair would serve as our fourth substituent there. Okay, an even more oxidized form of a sulfoxide is a sulfone. Okay, sulfoxide is much more polar and much more water soluble than a sulfone. Here we have this zwitterionic structure, and the oxygen is actually fairly basic, so it can go out and make a relatively strong hydrogen bond. Okay, so look what happens to the boiling point as we increase the oxidation level at sulfur. Okay, dimethyl sulfides 37 boils right at ideal body temperature, whereas the DMSO, or dimethyl sulfoxide, boils very high, 189 degrees. Dimethyl sulfide is not water soluble. Dimethyl sulfoxide, however, is completely water soluble. Okay, the boiling point increases a little bit further if you add the extra oxygen, but the water solubility actually goes down. This is because these oxygens aren't quite as basic, and they don't form quite as good a hydrogen bond as they do in the sulfoxide. Okay, let's look at the reactions of sulfides. We're going to find that they're actually very different from ethers. Okay, sulfides actually undergo alkylation reactions with really good or really reactive halides like methyl, benzyl, and allyl halides. Okay, so these can undergo the SN2 reaction with these very activated systems to form sulfonium salts. Okay? All right, so an example of this would be the reaction we show here, where dimethyl sulfide reacts with benzyl bromide to make the sulfonium salt shown there. Okay? So sulfides can be oxidized to the sulfoxides or to the sulfones. It all depends on how much oxidizing agent you have. This milder oxidizing agent, sodium periodate, actually stops there at the sulfoxide. But if we add hydrogen peroxide in 1 mole, we will get the sulfoxide. And if we add a large excess of hydrogen peroxide, it'll go all the way to the sulfone. Okay, unlike oxygen ethers, sulfur ethers or sulfides can undergo oxidation chemistry quite readily. All right, so a sulfonium salt is important in one of the fundamental biological transformations. This compound here is called S-adenosylmethionine. And this is the biological equivalent to methyl iodide. Okay, so we're going to say this is the okay, but methyl iodide would not be a good methylating agent in a biological system. It could react with any sulfur or nitrogen or alkoxide compound, basically anything that could do that has a lone pair that could do an SN2 reaction could react with methyl iodide. But the S-adenosylmethionine is much less reactive. In fact, it requires an enzyme to activate to get the substrate and the methylating agent together. An important biological transition is norepinephrine into epinephrine, and this occurs by an appropriate enzyme reacting with S-adenosylmethionine, and this nitrogen here, we'll just draw a fancy SN2 arrow, gets methylated like that, and that produces the epinephrine after you remove the extra proton from this initial SN2 adduct right here. Okay? All right. So I think, yeah, let's one other topic about ethers, and that is spectroscopy. Okay. All right, so normally we talk about the infrared, proton, and C13 spectra of these functional groups as we cover it. Here, infrared for ethers just really isn't all that useful. What we look for really is the absence of OHs and C double bond Os when we have an oxygen in the formula, and that's often a clue that you have an ether. So we're not really looking for anything, we're looking to see if other things are not there. That's how we identify ethers. Okay, all right, so like alcohols you've seen before, this hydrogen that's on the same carbon as an oxygen is going to occur at 3 to 4.5 ppm. All right, so we'll call this HA. There's two different ones in this molecule. We'll call these HB. All right, so here's HA. It's a singlet. And we predict that right, it's too far away from any other hydrogen to couple. Okay, it's slightly out of this range here of 3 to 4.5, and this is because it's also benzylic. And remember, in the NMR discussions we had previously, that a benzylic hydrogen is going to have a slightly higher chemical shift than the analogous hydrogen that if you had a cyclohexane, for example, there instead of a benzene. Okay, this triplet here at about 3.4, this is HB, and this is a triplet because it's coupled to the protons at HC. So this is another giveaway that for an ether you have two sets of these hydrogens that have the chemical shift between 3 and 4.5. Okay, in C13 NMR, we have two carbons attached to oxygen. So, for example, this benzyl butyl ether that you see here is going to have two carbons that look like they have chemical shifts for a carbon, sp3 carbon attached to oxygen. Basically, we're not seeing anything that different here than what we saw with alcohols. In fact, it's really hard to distinguish an alcohol from an ether by C13 NMR. The only difference is that you have two. If you have an unsymmetrical ether, you will have two of these types of carbons in your molecule. Okay, whereas in an alcohol, you would only have one of them. Okay, all right, so this is where I'm going to stop this video, and that's the last of the ether videos. Okay.